Everyone. Okay, let's get set up here. All right. Hope everyone felt okay about Project 3. We'll try to get those grades back to you in the next couple weeks. Let me know if you're having any trouble finishing, or if you've already talked to me about an extension, then that's obviously totally fine. Okay, yeah, homework 10 also, please try to get it in today or sometime this week. The homework and lab for this coming week is up. This is actually the second to last lab, and I think one of the last few homeworks as well. Okay, so today we're continuing talking about some kind of general issues in statistics, and so and again, this is just going to be a kind of high level overview of some of these concepts. And so what we're talking about today is effect size, which is something that we've brought up in a few different contexts. We've spent a lot of time talking about things like p-values, right? So when we do null hypothesis significance testing, what we get out is we want to try to make an answer. We're trying to get this binary answer of, is there any effect different from the null hypothesis, or does it look like the null hypothesis is a good explanation for this data? And so this is one of the main ways that we do statistics. It can be useful for lots of questions, right, about asking whether things are related or not. But it doesn't actually tell us anything about whether this effect that we're measuring is actually interesting or not, right? So this binary question of, is this effect exactly zero or not, might not be like the practically useful question. So for example, maybe we could figure out that a certain diet has an impact on your risk of heart disease, but maybe the impact is so tiny and the diet is so restrictive that no one would ever actually choose to do this, right? And so there's could also be things like it could also be that there's cases where things are important but hard to get a good p-value for. So for example, if you maybe there's something like, right, a small increase in risk of birth defects is something that we would care about a lot, but maybe this effect is so small that it would be hard for us to actually do a null hypothesis test where we get a really concrete answer, right? But we might still care about it even if it's not significant, right? So there's these issues of sort of uncertainty and importance and significance, which are all different concepts. Yeah, I mentioned the diet one before in the context of bacon. Well, bacon does maybe have enough of an impact on health that some people may choose to avoid it, but it is in this category of things where we are sure that it's bad for you, but we're just as sure that bacon is bad for you as we're sure that smoking is bad for you, for example. But smoking is much worse for you than bacon, for example. So the idea is that when we're reporting on some results, when we're trying to describe some data that we have, in addition to this significance test, we also want to say something about how big the actual effect is in this sample, and maybe try to say something about how big we think the effect is in the population. And sometimes those could be different things. Okay, so there's a bunch of different ways of measuring effect sizes. And again, when I'm saying effect size, all we're talking about is how big of an effect there is in the data. This is usually going to mean like how far away from the null do we think our data is. And so these effect sizes, one critical difference here versus p-values is that effect sizes are some measure of what we think is going on in the population, meaning if we take like a single sample, a single data point from our population, then we want to say something about how significant, how large this effect is. Right, and so I'll try to make the difference between these things clear, right? But when we're measuring significance, that's going to depend a lot on how big our sample is. Having a bigger sample is going to give us more precision and make it easier to reject the null hypothesis if it's not true. But these effect size measures are not related to the sample size that we're getting. This is really about how big do we think this effect is in a single data point we're drawing from the population. And so just knowing that something is significant doesn't really tell us. It could be hard to make practical decisions based on this because it doesn't tell us how big the effect size is. And so, for example, if there is a real effect, so meaning if the null is not true, then we will always be able to get a p-value that goes below our 0.05 threshold or goes below any threshold, as long as our sample size is big enough. So if we can keep drawing independent random samples from this population, we will eventually be able to say with confidence that the null hypothesis is not true. Right, but so what this means is that if you just have a p-value of 0.01 or something, that doesn't tell you whether the effect is big or small, right? It will be easier to get small p-values for big effects, right? They'll be easier to detect, and that's something we're going to talk about on Thursday. But just the p-value alone doesn't tell you anything about how big the effect is. But we still need the p-values, right? So just having an effect size alone doesn't necessarily tell us whether this effect is real or not, right? If we just take a sample, it looks like there's some big effect in our sample, but there's also lots of variability in our sample, then we might want to be unsure about whether this effect is real or not. And in fact, as we'll talk about a little more on Thursday, that having big effects is actually often the sign of an experiment being imprecise. We mentioned this also in the context of things like looking at results in small schools versus large schools, that small schools will often tend to have very extreme, either extremely good or extremely poor test scores just because they're a lot smaller. And so they it's much more likely for them to have these extreme results. And so just seeing that a result is really big doesn't necessarily tell you if it's a statistical fluke or if this is a real thing in the population, right? So the idea is that these are complementary things. There's getting the p-values, which tells us, do we think there's anything here or not? And then there's an effect size, which is how big is this thing that we found? Okay, so we're going to talk today about a few different kinds of effect size metrics. So difference effects are effects that are measuring some kind of separation between groups. This could also be between a single group and a null. And they're kind of like a z-score. They have a similar kind of setup. And so this kind of difference score we're going to talk about is called Cohen's d. We'll also talk about effect size measures for correlations, where we want to look at the relationship between multiple variables. And we've already talked about some of these. So Pearson's R and Kramer's phi are in this category as measures of relationships between different kinds of variables. And then today we're also going to talk about eta squared and omega squared, which are the effect sizes we use for ANOVAs. And then finally, another way of talking about differences between conditions, and this is often in the context of nominal variables, are risk ratios and odds ratios. So, right, all of these things are all these kinds of measures of ways of measuring how strong some effect is, meaning how different two groups are, or how correlated two variables are, or how related two different nominal outcomes are. Okay. So we'll have our first quiz, and the question is, as our sample size gets larger, our effect size will increase, decrease, not change on average, just get more accurate, or C, slowly converge to be the same as a p-value. Okay, so what can we say about effect sizes? Okay, yeah, I see some C's, which is correct, right? So effect size is, for example, effect size would be how how much improvement in outcomes do we get when we give someone this drug, for example. And so if we give the drug to more and more people, we'll get a much better estimate of that. But that estimate is not going to increase over time, right? As we keep doing the experiment, our estimate of how much the drug helps or hurts is not going to increase over time. That's different than p-values, for example, right? For if there is or some real effect of the drug, and we keep collecting samples over time, our p-value is going to get smaller and smaller, right? We're going to be more and more sure. There's no change in average. What I mean is that when we collect our first set of a few subjects and we see how well the drug works for them, and then we collect 100 subjects and see how well the drug works for them, there's not going to be any systematic relationship, right? So with those first 3 subjects, our estimate is going to be kind of imprecise, but it might be too high or it might be too low, right? And so over time, our effect size might go up or down as we're estimating it more and more precisely, but there isn't any systematic relationship with sample size, whereas there is for p-values, right? For p-values, if there is a real effect, then our p-value is going to get smaller and smaller with bigger samples. If there isn't a real effect, then our p-value is going to kind of just wander around, right, and be uniformly distributed like we talked about last week. Okay, so we're going to start with our first measure of effect size, which is called Cohen's d. And so this is relevant in the case where we are measuring some kind of separation between 2 groups. And so the idea is that there's some population effect size theta, which we define like this, which is the separation between the means of 2 groups divided by the true standard deviation in the population. Here we're using a pooled standard deviation, meaning we're just averaging the variances across the 2 groups. So this should look pretty much exactly like a z-score, right? We're measuring a difference between means in standard deviation units. We're asking how many standard deviations apart are these 2 means. Unfortunately, this is not something we know, right? Both the mu's here and the sigma are population parameters that we can't measure directly. So instead, we're going to do our best estimate from the sample. And so the sample estimated version of this is called Cohen's d. All we're doing is just plugging in our best guesses here. So instead of the true population means, we're going to plug in our sample means. And instead of the true population standard deviation, we're going to plug in our sample standard deviation. There's actually like a bunch of different versions of Cohen's d. This is the one for when you have 2 independent groups. And so we have a mean in group 1 and a separate mean in group 2. There's similar versions of this for like a 1 sample test or a paired test, for example. Okay, so so D here is our estimate of the sort of true effect size theta. The textbook uses this notation a little bit differently, but what you'd actually see in papers, again, is people would call this Cohen's d, and this thing on the right is the thing that we actually measure and report. And so, right, the idea here is we're asking how far apart the means of these groups are relative to the variation within the groups. And so in most things that we're measuring in the social sciences, this D is somewhere between like -1 and 1. The sign doesn't really matter here. The sign just depends on like which group we're considering positive and negative. But right, so we have Ds that are somewhere less than 1, meaning that these groups tend to be separated by less than 1 standard deviation. If they're separated by like 0.8 or more of a standard deviation, we'd say that that's a relatively large effect. 0.5 is like a medium effect. 0.2 is a small effect. These are not like official labels. This is just sort of within the literature. These is sort of the usual range of Ds that you might see. And again, we'll talk about this more on Thursday, but the bigger this D is, the easier it's going to be to detect a real effect, right? If the true effect is that the groups are very separated, right? The separation between their means is much bigger than the variation within the groups. That'll be easy to figure out with a small number of samples. So one thing I just want to to really point out again, because this is, I think, a common tripping point, is that Cohen's d looks really similar to a t statistic, but it's measuring something that means something different. So at least in the simple case where we're assuming the null difference is 0 and both of these groups have the same size, then Cohen's d looks like this, right? So it's the difference between the means divided by the pooled standard deviation. And so the way that we get a pooled standard deviation is we just average the variances in the two groups and then take the square root of those, right? So the way to get a pooled standard deviation is you have to pool the variances. So we average the variances in the two groups and then take the square root, right? So here's our Cohen's d. It's a difference in means divided by this standard deviation. The t statistic for how big the effect is in some particular sample looks like this, which is the difference in the means. The numerator here is the same, but the denominator here is not the standard deviation. It's the standard error of the sampling distribution. And right, the critical difference here is that instead of a 2, there's an n divided by 2 in the denominator down here. Right, so what the t statistic is telling us is that we have our sample mean, which is the mean of n, our n data points, right? How far apart is the mean of one group from the mean of our other group? And that difference in means is going to have a variability that scales with this standard error that depends on the sample size, right? So if we have very large samples, then the means of those of each group should vary very little. The means should be very close to the true population mean. And so the variation in those sample means should be pretty small, right? But this d here does not have an n in the formula, right? This d here is just saying if we take, this is just asking how far apart these populations are, right? These are the population, or at least our best estimate of the population means, and this is our estimate of the population variance, right? So it's kind of like we're just taking like one sample from each group or something, right? We're not averaging anything. It's just asking the distribution of things in population 1 and population 2, how far apart are those distributions, right? And so as t gets bigger, as n gets bigger, so as our sample size increases, all of these numbers are going to get more precise. So we're going to get better estimates of the means. We're going to get better estimates of the standard deviations. But this thing is not going to like consistently go up or down with n, right? It's just going to get more accurate. This t, however, is going to go up with n, right? So there's an n in the denominator of the denominator here. So as n gets bigger, this standard error gets smaller and t gets bigger. Right, so d is normalizing by the standard deviation of the population. T is normalizing by the standard error of the sampling distribution of the mean, right? And so as n gets bigger and bigger, if there really is a true difference here, then t is going to get bigger and bigger as well, right? We're more and more sure that there is a difference. So t is this kind of significance measure of how sure are we that there is a difference. And as we get more data, we're going to get more and more sure. D is asking how big this difference is, and we'll get a better estimate of that, but how big the difference is not going to go up as we get more. It's not going to consistently go up with more samples. Okay, so let's look at one more visualization of this. Okay, so so I like this. This is like a really simple little applet here that I think is fun. So what this is showing is we have two groups. They're labeled control group and treatment group. And what we have control over with the slider here is how far apart these groups are. And so if I put the slider all the way over here, right, the groups are exactly on top of each other. This is a Cohen's d of 0. And then I can start moving them apart. And so in this simulation here, by default, the standard deviation of the populations here is 15. So a d of 1, for example, means that these populations are being put, they're being put 15 apart. So we have the controls are centered here at 100 and treatment is centered here at 115. Maybe these are a little too small for you to see, but and so, right, so Cohen's d here is measuring how many standard deviations apart are these populations. So first of all, you can see that for the range of Ds that we usually care about in psychology, these populations are pretty overlapping, right? So a D of 0.5 looks like this. There's some little stats at the bottom here. So for example, 80% of the area here is overlapping, right? So a D of 0.5 means that if you just take a few samples, it's going to really be unclear whether this is one population or two. And another number here, which we're going to talk about later in the lecture today, is this probability of superiority, which means if we take one person from the control group and one person from the treatment group, what's the chance that the treatment person is having a better outcome? And right, this is saying like 64% of the time. So that's not nothing, but it also means that that the rest of the time you're going to be the control group is going to look better than the treatment group, right? So for effects that are like all the way out here somewhere, so like D of like 2, for example, these are effects that are so large that we usually wouldn't even do an experiment because it would be sort of obvious, right? For effects that are this large, the chance of a superiority is 92%, meaning that if we take one control subject and one treatment subject, the treatment subject is almost always doing better, right? So you'd only need really, even with a few samples, you'd be able to figure this out. Usually the effects we're looking at are more subtle things, right? And so really even in the best case scenario, we're maybe looking at something like this, where there's a lot of overlap, but we can still detect a difference with enough subjects. Okay. All right, we're going to do one more quiz on Cohen's d. And again, if you have any other Cohen's d questions, feel free to ask them. All right, so the question is, which of these 4 will not tend to increase Cohen's d? Increasing the sample size, increasing the difference between the means, making each group more homogeneous, or D, decreasing measurement errors? Okay, so if we wanted to increase Cohen's d, which of these would we not do? Okay, great. All right, good. I'm seeing a lot of A's, right? And so that, right, as we increase our sample size, the size of the thing we're measuring is not going to consistently go up. It'll just get more accurate. One way we could increase Cohen's d would be by moving the groups farther apart. So if there was some way to increase the effectiveness of the treatment, that would increase Cohen's d. The other thing that can increase Cohen's d is if the variability within each group gets smaller. And so we could do that by making each group more homogeneous, for example, by trying to control all the kind of extraneous factors that we can so that there's as little variability inside each group as possible. And we can also try to measure whatever outcome we're measuring. We can try to measure it more precisely, right? Any measurement errors that we have are going to also make these groups more variable, right? They're going to spread out our outcomes, which we don't want, right? To get the biggest Cohen's d, we want the two groups to be very different, and we want there to be very little variation that's not related to the groups. Okay, so Cohen's d is a really great tool for this kind of data where we have either two groups that we're looking for a difference, or maybe just one group we're comparing to some null. But this Cohen's d can't work in a lot of other situations. So for example, if we're trying to measure the effect, the strength of some kind of linear relationship between two variables, if we're trying to measure the importance of some group label in an ANOVA, this Cohen's d isn't really relevant. And so a more general idea is to think about this concept of variance explained. And so we've talked about this in a couple contexts so far, but right, the general idea here is that we have some data and there's some uncertainty, meaning that there's some variance around the mean in this data. And so what we want to know is if we knew some additional variable, so say we knew which group this person's in, how much does that reduce our uncertainty? How much does that reduce our variance about our guess of what outcome this person is going to have? And the idea is that if knowing some information decreases the variance, right, so that explains variance in our data, that tells us that there's some relationship between that information and this outcome that we're measuring. So we've encountered two things that are sort of like this before. So one is Pearson's R, which is when we're measuring a correlation between two scale variables. We can compute this R measure. Again, it scales between -1 and 1 and tells us how strong of a linear relationship there is between the variables. There's also something kind of similar we talked about for in the chi-squared lecture with Kramer's phi, saying how strong of an association there is between nominal variables. And so these are both kind of in this category of asking how much information we gain about one variable by knowing a second variable. And they have this same kind of interpretation as Cohen's d, which is that they're measuring how strong of an effect there is. And the bigger this effect is, the easier it's going to be for us to find it in our sample. But just like with Cohen's d, right, these measures, the correlation is not going to keep getting bigger and bigger with bigger sample sizes. We might be more and more sure that the correlation is not zero, but the correlation is just going to stabilize it's going to get closer and closer to the true population value over time. And we also talked about this somewhat more general idea of variance explained. And right in the context of linear regression, this is the same number as just squaring our Pearson's R. But it's also this more general idea that, and this is the formula back from that linear models lecture, that the idea is that we look at how many errors we have based on some baseline model, which is a model where we just predict the mean, right? The sum of squared errors of the mean is basically just like the variance that's in the data. And then sum of squared errors of the residuals is asking, after we make our prediction, how much residual mistakes are there? And the idea is that if those residuals mistakes are really small, then that's a good thing, right? That means that we explained most of our data, most of the variance in our data by using this predictor variable, whatever it was, right? So this is a really general concept, right? This is sort of could work in any kind of modeling context where we have some model that's predicting things. We can just ask how big the residuals of that model are versus the original variance in the data. So for example, we can do something like this with ANOVAs. And so for when we do this in ANOVAs, this is called eta squared. So this squiggly end thing is an eta, and it's measuring the proportion of the variance that's explained by some group label in an ANOVA. And so it's interpreted basically like an R squared. And so this eta squared is asking what sum of squares in the data is related to this effect. So this effect, for example, could be the main effect of some group label. How much of the variance in the data is related to that group label versus the total sum of squares in the data, right? If you remember our like pie charts, right? This is asking how big that part of the pie related to the effect is compared to the whole pie. And so one nice thing is if you have your like ANOVA table, you can just plug in some values from the table to get this, right? So in the numerator is our F value, and the denominator is F plus a ratio of the degrees of freedom. And so at least for like a simple effect with K levels, right, it'll be that formula all the way on the right. This is a proportion, so it's always going to yield a value between 0 and 1. 0 means that this effect is not explaining any variance in the sample, that knowing this group label doesn't help you, doesn't improve your predictions at all about what the outcome is. A value of 1 means that you can make perfect predictions, right? So the variance in the data is entirely accounted for by these group labels. Now, one problem with eta squared is that this is describing this variance in the sample. And so what this means is that what's happening here is that we're using this data and we're looking at the mean of each group using this sample. And then we're going back and predicting this same data using these means that we just derived from this data. And so this is not a terrible, I mean, this is still a meaningful thing to do, right? But it's almost certainly going to be a biased overestimation of how good these predictors are going to be on a new sample from this population, right? There's this kind of overfitting problem that, especially if our groups are really small, if we only have a small number of subjects in each group, then if we take a mean of that small number of subjects and then use that mean to predict these same subjects we just derived the mean from, it's going to look very similar to them, right? It's going to be a good predictor because that's how we got it, right? We use these same subjects to make a prediction and then predicted back onto those same subjects, right? It's a little bit like the harking stuff that we talked about last time, that we sort of get to derive our hypothesis and test it on the same data. And so, yeah, so this, especially if you have like many groups, so like many levels of a group, this eta squared might not be a good estimate of how well your model would actually work in the population. It's almost certainly a biased estimate. So there's a bunch of ways to try to correct for this. One of them is this different effect size called omega squared. It's mostly unbiased, meaning that it's still biased, but less biased than eta squared. It has a few problems. One is that it's only valid under a number of assumptions in the ANOVA, and ANOVAs have many, many assumptions to begin with. And so I tend not to like this metric because it's very unlikely that data will really match all these assumptions. But if you really are satisfying all the ANOVA assumptions, then this could work. Another problem is that if your model is complicated, and we haven't talked so much about how ANOVAs can be complicated, but if you have like multiple interacting groups, for example, it's really hard to even figure out how to write this down. But if you're in this sort of simplest case, which is that you have a one-way ANOVA, meaning you have a single set of group labels and a single outcome, and all the groups are the same size, then the formula is pretty simple. So it's very similar to the eta squared formula, but you subtract 1 in the numerator and you add 1 to this the DF error in the denominator. So yeah, it's pretty similar. This is basically always going to be smaller than eta squared. Right? We're adjusting our effect size down by a little bit and trying to get a more unbiased measure of how much variance our group means would actually explain in a new sample. And so, I mean, another thing you can do here is actually predict variance in a new sample, right? So we could do something, we could do something sort of like this equation here, right? Where we in some new sample, we make some predictions, we see how big the residuals are in that new sample that we didn't use to actually compute these means, and then we can measure how well we do, right? So that's another option, is doing some kind of cross-validated thing where we make predictions in a new sample. That's not the traditional way that we do things in statistics, but as long as your data satisfies all the ANOVA assumptions, then this omega squared will be kind of an estimate on how well your model is going to generalize to a new sample. Okay, so having said all of that, what should you actually do in practice? And this might depend a lot on the situation, but in general, if you're using like a simple ANOVA where groups are equal or close to equal, then this omega squared is not that hard to calculate and it's less biased, and so it's probably a better choice. Right? I mean, the more general advice here is, as long as you're in a situation where using some tool is comfortable, you should use the best tool that you can. But if you're in a complicated situation, for example, there's a whole other set of ANOVAs called hierarchical models, which we haven't talked about yet, but where you have like nested groups and subgroups inside of groups. And so in that case, even computing this omega squared is really hard. And so in that case, right, the advice might be to just sort of fall back on these simpler effect size measures, right? Fall back on these simpler tools that we sort of know what the problems are with them, right? But at least we know how to interpret them. And so, again, this is a sort of judgment call whenever we're doing statistics, is how fancy of tools do we want to try to use? The fancy tools can almost certainly give us better estimates of things, but we have to understand how to use them, and we have to understand what they're telling us, which we might not, either if we haven't learned enough about them, or it might be that some of these things are also just inherently complicated, and so it's just inherently hard to interpret what comes out of them, because it's a very complicated function of the data that comes in. Okay, so at least for eta squared, right? So this eta squared effect size value, if that value gets close to 1, what does that tell us? A, that the effect of the group label is small. B, that the group means predict most of the variance in the sample. C, that the group means would predict most of the variance in the population. Or D, that the group sizes are similar. Okay, so how should we interpret eta squared? And can you remember which one is which? Okay, so yeah, I'm seeing C's and B's, and remembering these symbols is also a bit tricky. So let me go back through the slides one more time here. So, right, the first measure I introduced was eta squared, which is this is the sort of more traditional ANOVA measurement, which is measuring in this particular sample how much of the variance can we explain with these means, right? We're going to derive the means from the sample and then predict back in the same sample. The more sophisticated thing here is omega squared, where we're trying to predict how much variance we would explain in a new sample that we didn't derive these means from. Right, and so the answer to the quiz here is that an eta squared close to 1 is B, which is saying that the group means are predicting most of the variance in this sample. Right, so eta squared value close to 1 means that the effect of the group label in our ANOVA is large, right? That this group label is explaining most of the variance in this particular sample. It doesn't necessarily tell us about C, right? So it's probably true that this would also work well in the population, but to do that, we'd really have to compute either an omega squared or some other kind of measure of generalization performance of how well we think this would work in the population. So for example, if you just had a data set where there's just 2 people and each one was labeled group A and one was labeled group B, in that case, eta squared would be 1. Well, it might be undefined depending on how you try the formulas, but yeah, so eta squared there is basically 1, meaning that if we take a mean of the one person in group B, that mean is perfectly predictive of that one person, right? But so that our eta squared there would be 1, but it wouldn't be super meaningful, right? It is true that in this sample, those means are perfect predictors of the data, but it doesn't really tell us anything about whether this model would work in the population, right? And so again, eta squared is sort of the more traditional and like easier to compute thing for ANOVAs, but we have to be a little careful, especially if our data set sizes are small, that it doesn't really guarantee us that effect size is true in the population. It might be that we're always going to be at least somewhat biased about how big that effect size is. Okay. So we're going to move on to another category of effect sizes here, which are usually talked about in terms of risk. Part of this is because they come mainly from the medical literature. And the idea here is that we wanted to figure out the relationship between some kind of factor and the risk of some kind of outcome. Right. And so the idea here is we're usually interested in some kind of intervention, for example, that could have some kind of impact on some bad thing that we don't want to happen, right? So we're talking about what's the risk of that bad outcome happening based on something else that we know about these people. So we want to know, right, are certain diets related to increasing risk of depression? If we introduced some kind of public policy like needle exchanges, is that going to change the risk of contracting HIV? And so usually the way we're going to drive effect measures here are going to be from contingency tables. And these are kind of similar to what we looked at in the chi-squared lecture, where we have people in the rows here, people that are in different groups. And so this group might be people like on a low sugar diet versus a high sugar diet, for example, or maybe a county that has a needle exchange versus one that doesn't. And then in the columns here, we have our outcomes, right? So we have hits, meaning the outcome occurred, and miss, meaning the outcome didn't occur, right? So what gets defined as hits and misses kind of depends on the situation. Usually hits here is like, in a medical context, the hit usually means that some kind of bad outcome is happening. So we have these 4 different frequency numbers, right? That's counting up how many people there are in each of these 4 situations, right? So we're dividing both by group as well as by outcome. So so one thing we could do here, like we talked about in the chi-squared class, is you could do some kind of test of independence here. You could also do and so the test of independence would tell us how sure we are that there's some relationship between the groups and the outcomes, which again is good, but it doesn't tell us how big the effect is. We could use the Kramer's phi measure we talked about. That is a true effect size measure in that it tells us how big the effect is. And another thing we could do is compute what's called a risk ratio. This is another measure of effect size. And so what we do to compute a risk ratio is we're computing the chance of this bad outcome in group 1 versus the chance of this bad outcome in group 2, right? So the numerator here is in group 1, how many hits were there compared to the total size of group 1? How many hits were there in group 2 compared to the total size of group 2, right? So you could also think about this as what proportion of people in group 1 are having this bad outcome versus the proportion of people in group 2 that are having this bad outcome. And so, and so the translation here, right, is we're looking at this ratio of risks, right? So when we say risk ratio, we're asking what's the probability of risk in one group, the ratio of that compared to the probability of risk in another group. Another way we can summarize these tables is by using an odds ratio. And so this is not super intuitive, but this is the one that statisticians tend to like because it's a lot easier to do things like hypothesis tests on. And so what we do here is we compare the ratio of hits versus misses in group 1 to the ratio of hits to misses in group 2, right? So we compute the odds of of this outcome in group 1. And so, right, odds here means we compare the counts of people having this outcome versus the people that don't have this outcome. Right, and we get the odds in group 1 and compare them to the odds in group 2. So for example, the odds in group 1 might be something like 2 to 1, meaning that there's twice as much of a chance of having a hit than a miss. The odds could be something like 1 to 1, meaning that you have an equal chance of the hits or miss outcome, or they could be 1 to 2, meaning that the hits are less frequent than the misses, right? So we compute these odds in group 1 and the odds in group 2, and then and divide those two odd ratios. So when hits are rare, then this formula is pretty much the same as the risk ratio one, because if almost everyone in the population is a miss, then whether you divide by the misses or whether you divide by the total population is basically the same. But as the hits and misses get closer to each other, then this odds ratio formula becomes very different from the risk ratio one. And so, yeah, at least in statistics, we often like to use odds ratios. You'll see why in a few slides. There's some nice formulas we can do with these. They also are, once you know how to interpret them, they are in some ways are easier to interpret for certain kinds of relationships. So, for example, here's some data of these are people that are at a substance use treatment facility, and what we want to know is among the people that are in this facility, is there a relationship between people being diagnosed with psychosis and people being diagnosed with major depression? And so we have our little contingency table like this, right? And so again, we are splitting people up here based on these two different factors, and we have counts here of each of the factors. Along the edge here are just the totals among the columns and the rows. Okay, so again, with this kind of data, we could do a chi-squared test to measure to see if there is a significant relationship or not. But with these effect size measures, right, we just want to measure how big of a relationship is there in this sample, right? It's not going to tell us if we're confident that it's a real relationship, right? If we're confident that it's different from zero, but it will give us a measure of how strong this relationship is, which might be clinically important, for example. So when we're computing this odds ratio, we have to sort of pick like which of these axes is the groups and which of them is the hits and misses. Although as you'll see in a minute, it actually doesn't matter what choice we make. So for example, one thing we could do is say, okay, what we're going to do is we're going to look at the psychosis diagnosis as the groups. So we're going to look at among people that are not diagnosed with psychosis, what number of them have depression versus don't, right? So we're going to compute odds ratios for depression within this psychosis group and within the no psychosis group. So, right, if we're just plugging numbers here, that says inside the psychosis group, the ratio of depression to non-depression is 29 to 46. Inside the no psychosis group, the ratio of depression to no depression is 108 to 456. Right, so you can see this one's about like a half, this one's about like a quarter. And so this gives us an odds ratio of 2.66, saying that, right, what this says is that if you are in this psychosis group, the odds of having depression are 2.66 times higher. We could have actually chosen to do it the other way. So instead of looking at each of these rows, we instead looked at the columns. So we could look among the people diagnosed with depression, what are the odds of having psychosis? And so that would be 29 versus 108. And then we could look among people not diagnosed with depression, what's the chance of having psychosis, which is 46 over 456. And so if we do things this way, we also get the same exact answer here. So this is a nice thing about odds ratios, is that for measuring relationships between these two groups, they're kind of symmetric. It doesn't actually matter like which group we take to be X and Y. And that's not true of risk ratios, right? For risk ratios, you have to specify one of these things as the groups and one of them as the hits, and that will give you different answers. That's also not generally true for conditional probabilities, right? For conditional probabilities are not symmetric. If we say the probability of A given B is not the same as B given A. Right, so this is one nice thing about these odds ratios. Again, they're like a slightly weird thing to interpret, but they're giving us a measure of how strongly related these two things are. So you can actually, we're mostly talking today about effect sizes and not hypothesis tests, but it actually is possible to do hypothesis tests on these odds ratios as well. So the null hypothesis here would usually be that the odds ratio is 1, meaning that the odds of having a hit in group 1 is the same as having the odds of a hit in group 2. The way we usually do hypotheses tests on these is we actually take the log of the odds ratio. So we're taking the natural log of the odds ratio. So these log odds ratio values, the null here is going to be the log of 1, which is 0. Right, so the null hypothesis is that log odds ratio is 0. We can then basically use a z-test here where we compare the log odds ratio that we actually have in our data to the null log odds ratio, which again is usually 0. And then we just need to divide by this sampling error in the data, which is given by this weird formula. So yeah, so you won't have to do this. I just wanted to mention that it is possible to use odds ratios both as an effect size measure, and then you can do some significance testing on them to say whether this odds ratio is significantly different from 1 or not. Okay, let's do a quick computation here. Okay, so this is data. This is well, it's from an old study, but this is real data of people. So they had a bunch of patients in the hospital that were being admitted for a number of reasons. Some of them were being admitted for esophageal cancer, and others were sort of control cases in the community. And so they categorize people based on are they heavy or light drinkers, and then each person is getting categorized into one of these 4 boxes, right? Are they getting this cancer diagnosis, and how much alcohol are they drinking per day? So the question is, if we wanted to compute odds ratios, right, in this 2x2 grid, right, what we're going to want to do is right, we're going to want to look at the odds. Well, we could do this a couple of different ways, right, but and get the same answer. But the way I'm assuming for this quiz is we're going to take these two different groups of people that are light drinkers and heavy drinkers. Within each of the groups, we're going to compute an odds ratio, right? So we're going to compute what's the cancer versus no cancer odds ratio in the heavy drinking group, what's the cancer versus no cancer odds ratio in the light drinking group, and then we're going to compare those two ratios, right? So which of these four would give us the result that we want to get an odds ratio? All right, I see some D's, which is correct, right? So what we would do here is, so within the heavy drinking group, the odds of cancer versus no cancer is 96 to 109, right? And so what this says is that of the heavy drinkers, the odds of having cancer are about 1-to-1, right? It's about equally likely to have cancer versus not have cancer in this group. In this light drinker group, there's the ratio of cancer to non-cancer is 104 to 666, right? And so there's a ratio here of close to 1-to-6, right? Meaning that you're about 6 times as likely to not have cancer if you're one of the people in this group. And so the odds ratio is just the ratio of these two odds. So and so the odds ratio here, again, is something like, this is like sort of close to 1, this is close to 6, so we end up with 5.6 here. Right, so what this says is that the odds ratio here that's comparing the relationship between cancer and drinking, right, is this is a relatively large value, right? It's saying that there's a big shift in your odds of having cancer depending on which group you're in. Of course, this was not a randomized study, right? This is an observational study. It doesn't mean that you could actually change your risk of cancer by switching yourself between these groups on purpose, right? It might be that, right, the people in this cancer group are having cancer is in some way related to drinking more alcohol in a way that's not causal from the alcohol, right? But this again gives us a measure of effect size, and this is a relatively large odds ratio kind of effect size, arguing that there's a big shift in cancer incidence between these two groups. Okay. So it might seem like there's a lot of ways of measuring effect size, and there absolutely is. And in fact, there's actually like lots of other ones that we're not talking about today. And the somewhat more troubling thing is that people don't even really agree about how you should be measuring effect sizes. So for example, Cohen's d, there's like at least 6 different versions of Cohen's d that are all measuring something really similar. They basically just get like normalized a little bit differently, and they make a little bit different assumptions about what your data populations look like. And so there's basically this like huge zoo of effect sizes that people report. Not all of them are even directly comparable to each other. So if you have 2 different studies using 2 different effect sizes, it's hard to even know which one is stronger. So this is kind of disappointing, because part of the whole point of these effect sizes is to communicate to people about the outcomes of these experiments, right, in a way that they could understand intuitively about how strong this relationship is. And so this makes it difficult for people that are reading these studies, right? You have to sort of know all these effect sizes. You have to figure out how to compare them. If we're trying to do like a meta-analysis of multiple papers, we need some way of getting these effect sizes all into some some kind of comparable framework. And so one thing that started to become popular over maybe the last 10 years or so is that for any effect size, we could convert it into a probability. And so this has a lot of advantages, one of which is that it's actually pretty easy to understand. So for example, if we think back to our like coffee tea example from a few lectures ago, we had people solving puzzles that were either tea drinkers or coffee drinkers. And so one way of reporting the effect size in that experiment would be to say the probability that a coffee drinker is faster than a tea drinker is 68%. This I think is pretty like, I mean, it gives at least a decent intuition for what's going on in this data set, right? It tells you that if you pick a coffee drinker and a tea drinker at random, that it's likely but not sure that the coffee drinker is going to be faster, right? And so I mentioned earlier in the lecture, this number is called the probability of superiority, which just means, right, what's the probability that a person from one group is going to be superior to the person in the other group. And so if there's no effect, if the groups are identical, this will be 50%, right? If there's no impact of your hot drink of choice and your puzzle solving, then the chance that that one person is going to be faster than another is just 50%, right? It's just random. A probability of superiority of 100% means that every single coffee drinker in the world is faster than every single tea drinker in the world, right? And again, this is not about means of the groups. This is about a single person from one group versus a single person from the other group. We might be very sure, right? We might be almost 100% sure that the means of these groups are different, right? But that's not what this is measuring. This is measuring just in the populations themselves, right? A single person from this population, how likely is it that the person in the faster group is actually going to be faster than the person in the slower group? And so now, if you remember back a few weeks ago when we did this, we actually failed to reject the null hypothesis here, right? Which maybe seems inconsistent with this statement that 68% of the time the coffee drinker is going to be faster. But what happened is that it wasn't that we didn't see any effect. It was just that we didn't get a p-value that was below 0.05, right? What we got is a t-statistic that was saying that in this sample, coffee drinkers are faster. But the t-statistic wasn't very high because there was also a lot of variability in the groups, right? So what we're saying here, and again, this is the difference between effect sizes and p-values, is that in this sample, the coffee drinkers did, on average, look faster, but there was enough variation in the groups that we're not sure this is true of the population, right? We're not. It could be possible that even with populations that were identical, it's possible we still could have gotten this result. Like 15% of the time, we still would have gotten this result, even if the null is true. So the way I can compute this 68% probability of superiority is first we get an effect size for coffee versus tea. This is a difference between two independent samples, so we can use the Cohen's d formula from the beginning of this lecture. And so, right, the Cohen's d formula, the numerator here is how far apart are the means, which in this case was like 37 seconds. So the coffee drinkers were 37 seconds faster at solving the puzzle. Then we put an estimate of pooled standard deviation on the bottom. And so to get a pooled standard deviation, we take the variances inside the two groups. We average those variances and then take the square root. So our pooled standard deviation estimate is like 56 seconds. And so this is 37 seconds divided by 56 seconds. And so we end up with this unitless d of 0.66, right? What this is saying is that the difference between the groups, so the speed up that we got in the coffee group versus the tea group is about 2/3 of a standard deviation. So this is our d, and to compute this to a probability of superiority, what we have to measure is we have to integrate the area under a standard normal distribution up to d divided by the square root of 2. So you shouldn't understand where that comes from. This basically just like gets derived out of the definition of probability superiority, right? But the idea is that we can just compute 0.66 divided by the square root of 2, which is 0.47, and we just look at the area under a standard normal from negative infinity up to 0.47, which is 68%. Right, so it should make sense that if you have a d of 0, then we're going to ask about the area under the standard normal from negative infinity up to 0, which is 50%. As d gets bigger and bigger, we're going to add in more and more of the area under this standard normal. Right, so again, you could do this in R using like the integrate function, or using the p norm function in R does the same thing as well. A sort of like quick trick you can do if you don't have R with you is that for the D's we usually deal with in psychology, you can actually just approximate this integral with this really simple linear formula, which is that, so if we have a D of 0.66, we just take 1/2 plus 0.66 divided by 2 root pi. So like in this example, if we plug that into this approximation, you get something that's not exactly right, but it's pretty close. Right, and so, again, what this shows you is that for a d of 0, we have a probability of superiority of 1/2, meaning that if coffee and tea drinkers don't differ here, then the chance of a coffee drinker being faster is just 50%. And as d gets bigger, this probability of superiority goes up. Right, once you can see, this formula can't work forever because eventually this will go above 1, which can't be right. But at least for small d's that are less than 1, this formula does a pretty good job. If you have really large d's, then you have to actually do it the real way. You have to actually compute area under the standard normal up to d divided by the square root of 2. Okay. So here's a quick check about this. So as Cohen's d goes from 0 up to infinity, what happens to the probability of superiority for one of the groups? It also goes from 0 to infinity. It goes from 0 to 100. 50 to 100, or 100 down to 0. All right, good. Yep, I'm seeing a lot of C's, which is right. So probability of superiority here will start from 50% is chance, meaning the groups are the same. If the groups are very far apart, meaning that D is going up to infinity, then the probability of superiority will be 100%, right? If D going to infinity means that the groups are infinitely far apart, that there's no overlap between the populations at all. And so if that's the case, that would mean that, for example, right, every coffee drinker is finishing the puzzle faster than every tea drinker. So that would be a very large D, and that would be a probability of superiority of 100%. Okay, so just to recap this one more time about effect size and significance, right, is that, right, we are getting the 68% here, which sounds like a relatively big number, but the problem is that there was a lot of uncertainty, right? This was a pretty small experiment, and so we couldn't rule out the possibility that that this difference in the means we saw in this sample was just due to sampling error, right? That if we reran this with a different sample, maybe we wouldn't get the same effect. But it wouldn't really be, when we fail to reject the null, we shouldn't say that we didn't observe any effect at all, right? Because we did observe one here, right? And D of 0.66 is actually like a decently sized effect for psychology. Right, so when we fail to reject the null, it's not proof that the null is true. It's just saying we don't have enough certainty in this data to really definitively say the null is false. Right, so there's what we're saying is that we're not sure what generated this data. It might have been the null, it might have been something else, right? And so this is a really important concept that is a common error people make in null hypothesis significance testing, is that getting a p-value that's above 0.05 doesn't really, we really can't conclude anything from that, right? All it tells us is that that in this particular sample, it could have come from the null, right? But it's not strong evidence in favor of the null necessarily. There's other kinds of techniques that we're not going to talk about in this class, but there are other kinds of techniques called equivalence tests, which are designed for really getting at whether this is evidence in favor of the null, or is it really just, it's not evidence in favor of anything because it's too uncertain. We will talk a little bit about this next week when we talk about Bayesian analyses. You can get things out of this Bayesian analysis that are actually telling you about something about the chance that the null is true. Something to keep in mind, again, for making actual decisions based on data, is that effect sizes can sometimes be almost more important than significance, right? That, right, there might be some kind of study that maybe it's a very tiny study because we didn't have the time or ability to do a big one, that maybe isn't like it isn't passing our significance tests, but we're seeing a really big effect size, right? You could also think about this as maybe there's a really big confidence interval. So maybe there's nothing, but maybe it's really, really bad. And that doesn't mean that it doesn't mean, okay, it's uncertain, we should ignore it, right? Maybe it means that we really need to devote more effort to studying this, right? Because maybe it's really bad even, right? And so, right, this is especially true with small samples where confidence intervals tend to be large. It's important to differentiate between we didn't get a small p-value here because it looks like the null is probably true, right? It looks like this data is inconsistent with there being a big effect of any kind, versus this data is consistent with both null effects as well as big effects, and we just don't know which it is, right? We need more data. And so, yes, this is, again, a common mistake people make is sort of thinking that p-values are the same thing as effect size, that small p-values mean the effect is big. P-values above 0.05 means that there isn't an effect, right? And that's not true. Our p-values are just telling us about the certainty we have that the effect is non-zero. If we want to say things about how big the effect is, we need to use these effect size measures. And so whenever we're looking at data, especially if it's data we're trying to make important decisions on, then most of the statistical techniques we talked about in the class are good for this second part about how confident we are that something happened. But we also shouldn't forget to actually talk about what happened, right? Meaning some measure of effect size that's some measure of the population. And right, and so the things we talked about today are in this category. Things like confidence intervals can also be in this category, right? Of saying some estimates of what possible values in the population are consistent with the data we saw in this sample. And so, yeah, so effect size metrics are answering this first question of how big of an effect are we seeing in the sample? And then all our measures of uncertainty, things like hypothesis tests and stuff, can address this second need. Confidence intervals can also really address both of these, I'd argue, right? Confidence intervals do also give us some information about how confident we are about what happened as well. Right, but just p-values alone really only address this second part. So as an example of this, in the 70s, there was a big debate about whether to allow cars to make right turns on red, which before that time in most places in the US was not allowed. So by default, if you came to a red light, you were not allowed to make a right turn on red. So we basically know now that this policy definitely increases traffic accidents. There's been a lot of studies of it over the past couple of decades. But when they were making a decision about this, this was partially driven by gasoline shortages in the 70s. There was a motivation to see if we should legalize this or not. And so they performed some traffic safety studies, and they did these in a number of ways. One way they did these was different states were legalizing right turns on red in different years. And so they could look to see, they basically looked at a few intersections before and after legalization in different years. And so here's some of the data that was used in this report. Right, they had a few intersections, and they looked at how many accidents there were before and after this right turn on red policy was enacted. I think the different years here are happening in different states that have different years of legalization. And so you can compute, for example, a risk ratio here, which is how between the two of these, right? What's are we seeing an increase or decrease here? And so you can see in all the places all the years are studying this, there's an increase in traffic accidents. But these samples are pretty tiny, and so the p-values here are not that impressive, right? They're not even really close to significance, right? And so in each case, accidents are increasing, but the studies were pretty small and none of them were statistically significant. And so that was used as an argument to say that there is no effect in this data, right? We're not there. We don't see any significant difference before and after legalization, which means that there's probably no effect. And so we should legalize this, right? It's going to help people get places faster. It's going to waste less gas. And again, since then, there's been a number of studies of this in much larger samples where, we now know that these risk ratios are, the risks are probably like at least this large in terms of increase in accidents, right? But the main message here is that, right, the reasoning here was not correct, which was that because we are not seeing significant p-values, that means that it's okay to do this, right? That we didn't detect a significant effect, which means that nothing's going to happen if we do this, right? And again, this is in this case, maybe it had more severe consequences, but this is a common mistake that people make in science all the time, is saying, right, these two conditions are significantly different. These two conditions are not significantly different. That means that the second pair is the same, right? And that's not what these tests are telling us. These measures of effect size can help us figure that out, right? Measuring an effect size can tell us how big of an effect we're seeing in the sample and what direction it's in. And p-values here are again, really most useful when we have enough data to really be certain about the outcome. Okay, so we've talked today about the difference between effect sizes and significance. Right, significance depends not only on whether or not we find a significant result, depends not only on the effect size, but also things like the sample size and what kind of analyses we choose to run. We talked through a bunch of effect size measures. So there are measures of association, association and correlation, which we've talked about before. There's similar kinds of metrics for ANOVAs. We can measure relationships between probabilistic outcomes. By far the most common one is just Cohen's d, which works whenever we have just one or two groups we're trying to compare. And then one way to try to make these effect sizes more unified and understandable is by unifying them through this probability framework, right? So in the slides, I just talked about how to do this for Cohen's d, but for basically all of these measures, we can compute this kind of probability of superiority of what fraction of the time would we actually see an effect in the correct direction if we sampled individuals from this population. And so even when we don't get a significant result, these effect size measures are really useful for telling us something about what we're seeing in our data. And when we do get a significant result, these effect size measures add a lot of information, right? Just saying that we're sure there's a difference might not be really actionable information, right? What we want to know is we're sure there's a difference and it's about this large. Then that can actually tell us whether it's worth implementing a policy change or trying to get people to implement a lifestyle change, right? Or is there some relationship between our psychological theory and this thing we're measuring in the brain, right? If we're sure there's a relationship, but we're also pretty sure that's very, very tiny, that might lead us to revise our theories about how the brain works. All right, any last questions? All right, so office hours and lab hours will be held as normal this week. Feel free to contact us if you need any help with the homeworks and labs. As we're getting close to the end of the semester here, right, please try to get in the homeworks and labs if you haven't already. The only sort of major thing that's left will be the final project 4, which will be after that last week of class. All right, great. See you on Thursday.